Hello everyone. This video is recorded for Hunt for India's Best Academic Project contest organized by crazyengineers.com. I am A. Santosh Kumar. My team members' names are H. Ritu and Shiny Prasanna. Our college name is Ishwari Engineering College from Chennai, Tamil Nadu. Our project title is EMG Controlled Self-Automated Prosthetic Arm for Physically Challenged.
The system components used here are EMG electrodes, ball bearings, dowel pins, and planetary motors. This project is about building a prototype of an efficient and low-cost prosthetic arm by measuring signals from the forearms using an EMG controller and EMG electrodes. The major system used is the 3D printing. The arm is made of plastic. The type of plastic used here for printing is ABS, which is a special material of very high strength. Here we can see the major part called the spool, which is placed attached to the shaft of the planetary motor in the motor housing. The nylon cable of 0.5 millimeters is passed through the spool. This causes a rotation motion. This is then passed through the grooved ball bearings for pulley action. Now the rotation motion of the spool is converted to linear motion by means of ball bearings when the motor is run. Here, the complete assembled arm is shown. The signals are passed to it from a microcontroller. Here, we are using an Atmega 328 IC. The signals measured by the EMG sensors are processed here based on the range required for each action measured and then is passed to the motor driver circuit. The EMG controller with its electrodes are shown here. The controller has 3 electrodes color-coded as blue, red and black. The red electrode or the signal electrode is usually placed at the center of the muscle on the forearms. It measures the voltage signals received by the muscles from the brain during a motion of the hand. The blue electrode or the reference electrode is usually placed at the end of the muscle. This is used to measure the reference signals of a particular action. The black electrode or the ground electrode is usually placed on the bones at the back of the arm. This measures constant signal, thus considering it as a count. Here, we can see the motion of the arm by measuring signals from the forearms. The first action shown here is a power grip. Based on the motion of the real arms, signals are detected and processed and the arm closes and opens accordingly. Using the action we are holding a screwdriver using the arm. The next motion is the active index grip. The signals are measured and thus making all the fingers to close except the index finger. There is only a slight bending of the index finger. This is usually used to carry a very small thread or so. This arm can be used by the general public who are physically challenged. By using 3D printing, the cost is drastically reduced. The existing system cost is around $11,000, that is approximately 12 lakhs Indian rupees. Thus, it becomes a lot more affordable to the general public. Apart from it, it also consists of efficient EMG sensors where the signals are measured in the range of millivolts. Thus, a perfect and normal working arm can be provided to the general public at a very low cost. Thus, in our existing system, we have produced around 3 degrees of freedom of motion in our project. Apart from this, our future goal is to bring around 70 degrees of freedom. Also, a more efficient design of the arm such that it will suit the original proportions of the user is also emphasized for our future goals. The strong reason why we propose our project should win the competition is because we have brought an highly efficient arm which will replace a human arm lost without much discomfort. Thus, we have brought an efficient prosthetic arm with EMG sensors of 90% efficiency and providing 3 degrees of freedom at a very low cost. Thus, our aim of making it easily affordable to the general public is accomplished here.